Balancing chemical equations, especially when we're working from naming to balancing chemical equations and writing chemical equations correctly. So when we look at this, we're going to have potassium, and we know that potassium has the chemical symbol K. Now, chlorate is going to be one of our polyatomic ions, so we have ClO3. Chlorate has a -1 charge, potassium has a +1 charge, so this would be the chemical formula of our chlorate, potassium chlorate. The metal gets listed first. So potassium chlorate yields potassium chloride, and then the word yield, it's or reacts to produce. This kind of word is going to show us when the reactants and the products end. So this means that in this chemical reaction, which is a chemical reaction where this potassium chloride will decompose into potassium chloride, so KCl. Now potassium once again has that +1 charge, and then if we look at the chlorine, so we know that this is chlorine. Is it a polyatomic ion? Is it the element chlorine? Because of the ending IDE, we can understand that this is the chloride ion. So it's the chlorine atom by itself. The chemical formula would be KCl because we have one ion of potassium and one ion of chlorine, plus oxygen. Now keep in mind that oxygen as an element will always be O2. So this is where our molecular elements like oxygen, nitrogen, chlorine, fluoride, iodine, they all will always be with the 2, right? We do not know the state of these, but that would be the next part of it. Did it start as a solid? Do we have a liquid? Do we have a gas? Do we have an aqueous solution, right? All right, so now that I have these elements, I can go ahead and think about balancing them. And I can make a list. I have potassium, I have chlorine, and I have oxygen. A way to balance them or to shorten this is that I've seen people let me just go ahead and put these guys in the middle. So I could also write them where I have potassium, chlorine, and oxygen. And then on each side, I can list how many moles I have. So in our reactant side, we have 1 mole of potassium, 1 mole of chlorine, and 3 moles of oxygen. Remember that those 3 moles are going to come from that subscript that we observe over there. Perfect. Then for our product side, we have 1 mole of potassium, 1 mole of chlorine, and 2 mole of oxygen. We're going to need to change the amount of oxygen in order to balance, since oxygen seems to be the one that it's not balanced. So let's go ahead and say, all right, so I'm going to add a coefficient of 2. If I add a coefficient of 2, it means that I'm changing the amounts of everything by a factor of 2. So now effectively I will have 2 moles of potassium, 2 moles of chlorine, and 6 moles of oxygen. To balance this on the other side, I'm going to need to add a coefficient of 2 in front of that KCl, which will increase the moles of each by a factor of 2, right? So 2 moles of potassium and 2 moles of chlorine. In order to have the same number of moles of oxygen on both sides of the equation, I am going to multiply by a factor of 3. So I put that coefficient of 3 in front, and then now I have the 6 moles, and my chemical equation is balanced. Additionally, we're going to go with that next element that we have over here. So we have aluminum acetate, right? And aluminum acetate, the ending ATE or ITE should indicate the presence of a polyatomic ion. Acetate has different ways that it can be written. More often than not, we can write it as like so. Right, so we can have that CH, the acetate, we can write it as CH3, COO, or sometimes you can see it as the C2H3OO. The acetate has a charge of -1 and aluminum has a 3 plus charge, right? It means that to write out the chemical formula, I'm gonna have to have 3 moles of that acetate for every 1 mole of the aluminum ions. Perfect. So aluminum acetate and potassium sulfate, potassium with a +1 charge, and sulfate is SO4 with a 2 negative charge. So we have our SO4 with a 2 negative charge, and this has a positive charge. If I'm just counting, I can see that I would need 2 of these potassium for every one in order to have a neutral charged compound, right? So it means that I'm going to need 2 moles of potassium for every 1 mole of sulfate. And then aluminum acetate and potassium acetate react, so that's what our plus tells us, to produce, so this is where our arrow will begin. And we're going to have potassium acetate, so KSO4. Remember that potassium will have that positive charge. And then we're going to have these, we're going to have potassium acetate. I knew I was doing something, potassium acetate. So we're going to have with the CH3COO. And potassium has the positive charge. Acetane has a -1 charge. We only need 1 mole of each. And aluminum, so aluminum with 3 plus and sulfate, SO4, 2 negative. Remember that when you're writing out, you do not need to write the charges. I'm writing the charges in order to decide what the correct chemical formula is. So I'm going to put this in parentheses because I'm going to need 3 moles of potassium of sulfate for every 2 moles of aluminum. If I were to look closely, you would see that the presence of this is going to give us a 6 plus charge with a 6 negative charge for a net 0. So let's keep that in mind when we're balancing when we're making sure that we have the correct subscripts. We are accounting for the correct number of ions or moles of every element in this compound, right? Okay, so now we need to go ahead and balance this chemical reaction. And this is a very good example of when do I need to list every single element individually, or when can I keep things as a group. So notice how we actually sulfate remains intact. We don't have any compound on the product side where sulfur maybe is by itself, or we have an SO2. We see this SO4 as a group remains the same. Then we also see that acetate ion also remaining together. So when that is the case, you can do that observation first, and you can list them as having aluminum. We have the acetate ion entirely, and we have potassium, and we have SO4. Then I don't have to worry about balancing each of these individually because it remains as a unit entirely. So I will look at my starting moles based on just the chemical formulas. We have 1 mole of aluminum, 3 moles of acetate, 2 moles of potassium, and 1 mole of sulfate. Then we can look at this aluminum over here, and we're going to have 2 moles of aluminum. We have 1 mole of that potassium sulfate, potassium acetate, and then for the sulfite, we have 3 moles. As you can see, our equation is not balanced, and I need to balance it. So in order to balance, I'm going to start with one of my metals to balance it. Let's go ahead and choose this aluminum to be balanced first. In order to have the same number of moles of aluminum in both sides of the equation, I need to equal this to 2, right? So let's say that I'm going to have that aluminum, and just preliminary looking, if I were to put a 2 in front of this, it would also change the amount of acetate in a total of 6, and therefore I will have to balance that. So remember that wherever you start, it will create a ripple effect of what needs to be balanced first, because this coefficient is going to affect everything that is in that chemical formula. All right, so I'm using a coefficient of 2, so I'm multiplying this by 2, and that means that I have 2 moles of aluminum, I have 6 moles of acetate. In order to balance this, on this side of the equation, my aluminum is now balanced, but I'm going to find where the acetate is. In order to get a total of 6, I'm going to have to multiply this by a factor of 6, right? And that means I'm going to put that 6 in front of here, and notice how it changes the moles of potassium and the moles of acetate. So I'm going to multiply by 6 similarly, and now I have those 6 moles of acetate, 6 moles of potassium. And I have now find what I need to balance next. In order to balance the number of potassium moles on the reactant side, I'm going to likely need to use a coefficient of 3. So I am going to multiply that 2 by a factor of 3. It will give me 6 moles. Effectively, this is also going to change the amounts of sulfate. And we have 3, and you are done, because if you notice now, your sulfate is balanced on both sides of the equation. Yay! Need to check to make sure that you have. As a reminder, you do not need to write, especially for balancing chemical equations, you do not need to write this out. I need you to be able to write those coefficients. This is a way for me to teach you how to keep track of the moles and find the factors or coefficients I need to multiply these by in order to have the same moles of each individual species on both sides of the equation. All right, so hopefully you work these ones on your own. If you didn't, pause the video, work through them, and check your work. So when we look at these, let's just point out something very specific that I want you to notice. And one of them is how when I have this type of reaction, this is called a combustion reaction. Combustion reaction, where we produce carbon dioxide and water as the products of the chemical reaction. We may look that we have larger moles, and keep in mind that the source of oxygen is oxygen in our air, and therefore when we're burning things, we're going to use as much oxygen as possible for the chemical reaction to take place entirely. So keep that in mind as you work through. I've forgotten to add that 2 over there. So don't be scared if you have large coefficients when you're balancing a chemical reaction. Additionally, I want you to notice how for oxygen right here, I kept tally of oxygen in 2 separate piles, because oxygen is present in this compound by a factor of 2, and it's present in this compound by a factor of 1. You don't want to add them up together and say that initially I have 3 moles, because you're not changing when you multiply by a factor here, right? When I multiply by this coefficient of 12, I'm only changing the amount of oxygen present in carbon dioxide. So as a strategy, you want to list them separately so that you can successfully look at them that way. Tally up and you have it all entirely. We have over here a metal reaction. This is a single displacement reaction is what it's called. So if you notice, the zinc is displacing the hydrogen and binding with the chlorine to form that chemical compound. Make sure you check your work. And this is it for balancing chemical reactions. Practice, practice, practice makes perfect. You will get the hang of it. Now, to finalize, why is this important? Because when we're looking at this, we are looking at wanting to focus on understanding the number of moles of each of these substances so that we can learn about the study of that numerical relationship between chemical quantities in a chemical reaction. And this is what it's called a stoichiometry. So, in this next part of our lecture, we're going to learn about a stoichiometry. And don't let the word confuse you, but a stoichiometry is going to be that study of the numerical relationship. So, we're going to look at the ratios, and we're always going to start a stoichiometry with a balanced chemical reaction. So, you need to master balancing chemical reactions as you move into a stoichiometry. Stoichiometry, and what are the learning targets of this portion of our lecture? We're looking to be able to define what stoichiometry is and why it is important. At the end of the day, stoichiometry allows us to make that mathematical connection, right? The numerical connection from a chemical reaction. We're going to need to do mole to mole conversions, mass to mole conversions, mass to mass conversions, and we're going to practice problem solving, which is going to stay with us for the rest of our Gen Chem course. So the coefficients in a chemical reaction, in a balanced chemical reaction, specify the relative amounts in moles of each of the substances that are involved in a chemical reaction. What does this mean? So let's look at this balanced chemical reaction between this compound, so C3H8. So this is our butane, and we're going to react it with 5 moles of oxygen to produce 3 moles of carbon dioxide and 4 moles of water. So we can view this chemical reaction in the following way. We can look first at it in terms of molecules, right? So I'm going to have 1 molecule of C3H8, and this is important because it also is telling me that I'm going to remember that we use the word molecule because this is a covalent compound. I'm going to have 5 molecules of oxygen, 3 molecules of carbon dioxide, and 4 molecules of water. I can also interpret that in terms of literally I am counting the number of molecules, right? So here we have 1 molecule of that butane, and then we have our 5 molecules of oxygen. When I also look at it in terms of amount, I am going to use the units of moles. So I'm going to have 1 mole of butane reacting with 5 moles of oxygen, 3 moles of carbon dioxide, and 4 moles of water. So ultimately, we want to be able to understand that regardless of which perspective I'm doing, in terms of amount, if I were to add up and I take the molar mass of every single element, I add them all up together, I am going to find that the total mass that I started with is the mass that I end with. And remember that this is obeying the law of conservation of mass. All right, so a chemical reaction tells us quite a bit, actually a lot, about this chemical process. When we look at it in terms of a molecule, this is a molecular level perspective of a chemical reaction, really helps us understand what all is going on. And I want you to take a minute and visualize what's going on over here. So this is telling me that I have 2 moles of H2O2, and that this hydrogen peroxide will decompose into 2 moles of water and 2 moles of oxygen and 1 mole of oxygen gas. Notice how I'm breaking bonds. So over here, I broke this oxygen-oxygen bond, right? And then I had one of these hydrogens kind of move over here and bind with the remaining oxygen. And then as this and this bond broke, I have a new bond that formed. So what this means that in a chemical reaction, what we're doing is the breaking bonds in my chemical reactants, and I am forming or making new bonds. And the change of breaking and forming bonds will explain the energy exchange that takes place in the chemical reaction. So where does calculations come into place? So we're going to look at these calculations of mole ratios. Let's focus on those coefficients and how I interpret this from a chemical reaction. So if I say how many moles of iron are needed for the reaction of 12 moles of oxygen, the first thing I'm going to need in order to answer this is to have a balanced chemical reaction. With this balanced chemical reaction, I'm saying, hey, iron is reacting with oxygen to produce iron oxide. Remember that this iron, because iron has more than one type of ions, this would be iron just a little bit adding iron 2 oxide would be the name of this compound, right? So the way I interpret those coefficients is that I am saying that the coefficients can be used to write this relationship of mole to moles, and I can use them as conversion factors. So this mole to mole connection is going to tell me that in those coefficients, I can potentially say that the ratio of oxygen to iron or iron to oxygen is that for every 3 moles of iron, every 4 moles of iron, 3 moles of oxygen are needed. The mole to mole relationships means that I can write this as a molar ratio. So the molar ratio is my conversion factor, right? So for every 4 moles of iron, I'm going to have 3 moles of oxygen. For every 3 moles of oxygen, I'm going to have 4 moles of iron. I can write 2 different conversion factors, right? Overall, if I had, let's say, the 12 moles, so let's solve our problem, right? So I have a starting amount. So this is my starting amount from the chemical problem, right? From the problem. I'm going to write my starting amount. And if you notice in this starting amount, we have moles of oxygen. Which of these 2 conversion factors would be the most appropriate for this calculation? You got it. I need to have moles of oxygen, right, at the bottom of my conversion factor so that the moles of oxygen cancel out and the moles of iron remain. It is very important that we label things correctly. So we cannot just write moles and we cannot just write 3Fe. It needs to include the units of moles. So with that conversion factor, I can let the units guide you to what conversion factor to use correctly. So in this process, I know that the moles and moles will cancel out and my remaining moles are going to be iron. So at the end of this, I'm going to have that 12 times 4 divided by 3, right? So far, in most of the conversion factors we've used, we had 1, right? Like 1 mole for every 2 moles. But because we're starting to add this molar ratio, you will not always have a 1-to-1. We're not going to have a 1-to-2, a 1-to-5. We're going to have, in this case, a 4-to-3. So remember that mathematically, we're multiplying this 12 times 4 divided by 3, and that's going to give us those 13 moles of iron. It must have 2 significant figures since we're accounting for significant figures, since the measured amounts given are in moles, right? Those 2 moles. Let's look at these practice problems. I want you to pause the video, work through it, right? Calculate the number of moles of HOCl to produce by from 0.12 moles of NCl3 by the following chemical reaction. As we work through this, now you know that you have notice how I'm intentionally, so strategies from problem solving, I'm intentionally wanting to highlight or underline the actual participants in my calculation. So I have moles of HOCl, so I'm going to underline that. And then I have moles of NCl3. So the only ratio that I am concerned about is the ratio of NCl3 to OHOCl, right? To that. So, and based on this balanced chemical reaction, for every 1 mole of this, I didn't leave enough space. For every 1 mole of this, I have 3 moles of HOCl, right? So I'm gonna bring that over here. For every 1 mole of NCl3, I produce 3 moles of HOCl. I cancel out those starting units from my starting amount, and I can go ahead and solve. To solve this, I'm going to have that 0.12 multiplied by the 3, and that's going to be my answer. Right, so we have that 0.36 moles of HOCl will be our answer. All right, so this would be perfect, right? We're all good to go. We can use the chemical reaction to do calculations. But what is the reality? The reality is that reactants and products are not measured in the units of moles in the lab. Solid usually are going to be measured with a balance, right? So in the balance, I'm going to measure that. Therefore, we must convert the grams to moles before we can use those stoichiometry relationships. How do we convert that? Great job. The molar mass. So our molar mass of our chemical compounds, the molar mass of our elements, right, or products, wherever we got over there, it's going to be that bridge to convert from moles to grams and vice versa. When it comes to liquids, if I have a liquid and I have a solution, I'm using a burette, I'm using a graduated cylinder to measure those moles, and therefore we need to have other conversion factors or other ways for me to convert this volume into moles, and we will learn more about that in our next module, which is calculations with those liquids. So let's go ahead and practice doing those. This is going to be a mole to grams or mole to mass calculation or mass to mass calculation, right? So mass to mole calculations. This means that I am using the molar mass of a chemical compound to convert whatever measure or starting amount from grams or milligrams or micrograms, whichever mass units I have, to moles. According to the following reaction, how many moles of H2O2 are required to react with 16.43 grams of N2H4? So if we look at our balanced chemical reaction, right? So we have this balanced chemical reaction. The first step is for us to get to moles using the molar mass. So remember reading the problem correctly. I want you to read the problem, I want you to pause the video, and I want you to try it on your own. So when I look at this H2O2, I'm going to find it, right? I'm going to have this H2O2, which is peroxide, hydrogen peroxide. I have it right here. And I'm going to find the other substance that I am concerned about, and it's going to be that 16.43 grams of dinitrogen, right? Here we go. Awesome. So I do not need to worry about the ratio of these two. So what is the ratio? What is the molar ratio? The molar ratio is telling me that for every 7, let's change this, for every 7 moles of H2O2, I need 1 mole of N2H4, right? However, if you notice, for our starting amount, so our starting amount is 16.43 grams of N2H4. And to get from grams to moles, I need to use the molar mass, right? Why moles? Keep in mind that I'm going to do moles because these are the units, and the only way I can do this ratio of one to the other in order to find out how many moles of hydrogen peroxide I need, right, is going to be through having the proper units first. So if we notice, once I have that molar mass, I know for every 1 mole of N2H4, I'm going to have 32.0452 grams. So 63.43 times 1 divided by that, it's going to be that 0.5127 moles. Step 2 is going to be for me to get that, right? So I'm going to generate the molar ratio. I'm going to use that molar ratio to convert to moles of substance A to substance B, which is, now that I have this moles, right, I'm going to have that 0.5127 moles of N2H4. And I'm going to use that molar ratio from the chemical reaction. Notice how my new starting amount is going to be the moles of N2H4, so dinitrogen tetrahydride. And so therefore I need to write that at the bottom. So I have that according to that molar ratio, which I have over here, for every 1 mole of N2H4, I produce 7 moles of H2O2. Cancel out the moles, and then you have your answer. And that's going to be the 3.589 moles of H2O2, that dihydrogen dioxide, or hydrogen peroxide, which is how we call it as well. Awesome. So if you notice, this is a apply and analyze. We are applying our knowledge of molar mass in the context of stoichiometry, where we're learning to use the molar ratio from a balanced chemical reaction to calculate moles of substance A to substance B. Let's go ahead and practice. So notice how you have your, the problem reads, according to the following equation, how many grams of aluminum bromide are formed by the reaction of 1.50 moles of HBr, right there. So strategy, underline with different colors to make sure that you can focus on those two substances. Write that ratio of one to the other, right? So I have these 6 moles of HBr for every 2 moles of aluminum bromide, right? Then I can look and see where am I going. Now to how I am, my starting amount, it's moles of HBr. So remember to always write your starting amount. And in this case is 1.50 moles of HBr. And then my calculated amount, right? The amount that I'm looking to get after I'm done with this calculation is grams of aluminum bromide. So I'm going from moles of substance A to grams of substance B. And there is not a one-step process. I'm actually going to need to do it in 2 steps. In the previous slide, in this slide, right, in that previous slide, we did it step 1, get 2 grams, step 2, use the mole, right? Let's put it all with our string of conversion factors and dimensional analysis. When I look at this, the first thing I'm going to need to go is to use the molar ratio from the chemical reaction, and we use the RxN to refer to that chemical reaction equation. And I need to have moles of HBr at the bottom, right? So that these two cancel out. And then I'm gonna have those moles. So let's keep the color coding. So there's 2 moles of there's 6 moles of HBr for every 2 moles of AlBr3. We cannot end here because our new units would be moles, and I am being asked to calculate the number of grams, right? So it means that I need to have this additional conversion factor right here, where I'm going to use the molar mass of AlBr3 of the aluminum bromide to find the grams, right? To go from moles to grams. All right, so we calculate that molar mass. We know that for every 1 mole of aluminum bromide, we have 266.68 grams of aluminum bromide. As a reminder, you would take, if you, like, how do I calculate that molar mass? Well, you know that you have in the chemical formula individually, not accounting for that 2 coefficient. Please, please, please. It's the molar mass is for 1 mole. So for every 1 mole of aluminum bromide, we have how many grams? It's always 1 mole. So we have aluminum and we have bromide, and we need 3 of these guys. Aluminum has that 26.98. And then bromide has 79.90. I will multiply this by 3, add it up together, and that's where we end up with our 266.68 grams. So after this is all done, you're going to have that 1.50 multiplied by 2 divided by 6 times 1, right? Divided by 266.68. And that's going to give me a total of 0.00187 grams of aluminum bromide. Perfect. As I had mentioned previously, we measure mass of reactants and we measure mass of our products. So the more realistic perspective or calculation, the more common calculation, it's actually going to be mass to mass stoichiometry. This means that I'm in this mass to mass stoichiometry, I'm looking at understanding that I'm usually going to have a starting mass of substance A, and I need to have it to the mass of A, right? And this mass of A will allow me to therefore use the molar mass of that compound to find the moles of A. Once I know the moles of A, I am then able to bring in the ratio from the chemical equation, right? And this ratio from the chemical equation allows me to go to moles of substance B. Once my chemical reaction takes place, right, my product, it's either going to be a solid or it's going to be a liquid, right? Or it's going to be a gas. So therefore, when I am measuring the amount that was produced, I am not going to be measuring in moles. I am going to be measuring in grams or in milliliters in one of our units of the measurements that we take, right? Depending on the form that it has. Therefore, in these calculations, I can determine the mass of B. So now, why do we do this? What is the purpose of these calculations? Well, you have to understand that a balanced chemical reaction allows me to predict in theory, meaning on paper, how much is needed of reactants and how much is produced of my products. So how much do I make? And this is where the money comes. No chemical process, no industrial process can undergo without me controlling the variables. I need to know how much of this do I need to weigh out so that I have my target amount of mass of B. Or if I want to minimize a waste, if I want to minimize the production of, for example, carbon dioxide to clean the air, I need to understand in a combustion reaction, in this chemical reaction, how much is produced to begin with, right? So the application of stoichiometry is as real as it gets to actually have an expected amount. In theory, how much should I get? Now, what we will do later on, and this is coming up soon, is that there is a difference between theory, sometimes can be the same as actual or real or experimental values. So these small mass to mass conversions, it's allow me to calculate in theory how much of each of these is produced. To find out in reality, I would have to actually go to the lab, carry out the chemical reaction, and extract my product and do the measurements, right? Perfect. Go ahead and practice. You have everything you need to be able to solve this problem. This is an opportunity for you to apply and analyze. Solutions of sodium hypochlorite are sold as laundry bleach. This is what bleach is made of. The following reaction makes this compound. How many grams of chlorine gas are needed to react with 60.9 grams of sodium hydroxide? I'm just going to get you started real quickly. I'm going to focus on the substances, find them. So I have NaCl, right? Perfect. And then I also know that I'm looking at how many grams of chlorine right here. And then I also have my grams of sodium hydroxide. Now, notice how solution of sodium hypochlorites are sold as laundry bleach. Really has nothing to do with my calculation, right? Because my question is actually having me look at that ratio of chlorine to hydroxide. Notice those starting values. I have grams of chlorine. I have grams. Let's take these out. I have those grams of chlorine gas. And I need to know, right? I'm starting with grams of sodium hydroxide. In order to use this molar ratio, I gotta take those grams to moles of OH and NaOH. And I need to take those moles of NaOH, 2 moles of chlorine gas, and from that 2 grams of chlorine gas, right? For step 1, I'm gonna use the molar mass of NaOH. From this is step 1, right? For step 2, I need to have the molar ratio from the chemical reaction, from the balanced chemical reaction. And then for moles of chlorine to grams of chlorine, I'm going to use that molar mass of chlorine gas, the Cl2. Go ahead and solve. All right, so once you complete the whole calculation, what you're going to understand and what we need to make the connection with is that now we're assuming that when this reaction takes place, I go to the balance, I weigh out 60.9 grams of sodium hydroxide, and the reaction takes place, I need to add at least 54 grams of chlorine in order to have this chemical reaction takes place. This is what this would look like in real life, right? So I can choose a starting amount, and then I'm going to need to calculate how much do I need of this other reactant for the reaction to take place. So this tells me this is the least amount that I need to add of chlorine gas in order for the 60.9 grams of sodium hydroxide to react. Mass to mass stoichiometry problem. So I want you to practice this. Phosgene was used in World War I as a war gas. It reacts with water in the lungs to produce HCl, which causes severe lung damage and ultimately leads to death. Isn't that cruel? Like, what the heck's war? How many grams of HCl are produced when 11.0 grams of carbon dioxide are simultaneously formed? So in here, I am wanting to look at those grams of HCl that are produced when 11 grams of carbon dioxide are produced, right? So my starting amount are going to be grams. The 11.0 grams of CO2 are my starting amount. And then my final amount that I'm looking to find is going to be those grams of HCl. I'm starting with grams of substance A. I need to find grams of substance B. I need to go from grams to moles, from moles to moles, moles of A to moles of B, from moles of B to grams of B to get there. Go ahead and calculate that. In that first step, you're going to use the molar mass of CO2. You have to calculate it in this example, right? I'm going to calculate the molar mass of CO2, and I'm going to use that. So I have the molar mass to go from grams to moles. Based on the balanced chemical reaction, I know that the ratio, remember we have moles of CO2, so I need to write moles of CO2 at the bottom. For every 1 mole of CO2, I will produce as well 2 moles of HCl, of the hydrochloric acid. Moles and moles of CO2, carbon dioxide gets cancelled out. And then I'm going to use that molar mass of HCl. So I know for every 1 mole of HCl, I have a total mass of 36.46 grams of HCl. So grams of HCl and grams of HCl cancel out, and I'm able to do my calculation. And this is going to give us that 18.2 grams of HCl. Now you want to make sure that you are following along, also practice with your active homework to ensure that we are keeping up and understanding what we're working with, right? Perfect.